If two things happen at the same time, they are said to occur simultaneously. In this lecture, we explore how simultaneous events appear from different inertial reference frames. We will use Einstein's postulates and the results we derived for time dilation and length contraction. Let's consider two observers. Mr. Red and Ms. Blue are standing at opposite ends of a train car. The train is moving to the right with velocity v equals 1/2 c relative to the ground. A timer is attached to the train and moves with the two observers. A flash bulb is placed halfway between Mr. Red and Ms. Blue. When the flash bulb goes off, a spherical light wave will travel outward and the timer will start. Let's put it in motion. In the train's reference frame, the train is at rest and the ground is moving to the left. The light is going to turn on right now, and you can see the circular light wave moving outward. It reaches our two observers at the same time right here. Let's briefly pause the simulation. Notice the light wave arrived at each observer at time t prime equals 5. Now let's watch the same scene from the ground frame of reference. The timer is now attached to the ground instead of the train. It might be hard to tell, but the train is compressed slightly due to length contraction. Since v equals 1/2 c, the gamma factor is 1.15, so the length of the train is about 86% its rest length. You might notice that Mr. Red and Ms. Blue have slightly oval heads instead of circular heads when they were at rest. Let's watch what happens. Mr. Red travels towards the light source while Ms. Blue is moving away from it. Mr. Red will see the light flash right here, but the light wave is still trying to catch up to Ms. Blue. She will see the light flash right now. Thus, in the reference frame of the ground, Mr. Red clearly sees the light flash before Ms. Blue. However, in the reference frame of the train, they see the flash at the same time. So who's correct? The amazing answer is that both perspectives are equally valid. Simultaneity is relative. Some observers might see two events happening at the same time, while others will see one event happening before or after the other, depending on one's relative velocity. Before we analyze this scenario mathematically, let's first introduce something called a spacetime or Minkowski diagram. In calculus or in intro physics, we are used to making position time plots, where the position of the object is plotted on the vertical axis and time runs along the horizontal axis. In this kind of plot, the velocity is the slope of the x versus t curve. A spacetime diagram differs from a position time diagram in two ways. First, we plot time on the vertical axis and space on the horizontal axis, so the axes are exchanged. Secondly, time is multiplied by the speed of light. The quantity ct has units of length and is equal to the distance light travels in a time t. The path of a particle in this diagram is sometimes called its world line. So instead of trajectories starting at the left-hand side and evolving to the right as time goes by on a normal position time diagram, now particles start on the x-axis and evolve upward through time like this. The slope of a line in this diagram is proportional to 1 over the velocity. So imagine we had a world line with a constant slope, then the change in height would be c delta t, and the change in the horizontal axis is delta x. So in this case, the slope is equal to c delta t over delta x, but delta t over delta x is just 1 over the velocity. In this lecture, we'll be using the quantity beta throughout to make things a little bit simpler. So we can also write this as 1 over beta, where again we've defined beta as the velocity over the speed of light. So let's consider a particle that starts at the origin. So it starts at x equals 0 at time t equals 0. Everything in the top half of the plane happens in the particle's future, and everything in the bottom half represents the particle's past. So let's look at some examples, remembering that the slope equals c over v, which is the same as 1 over beta. When a particle is at rest, the velocity is equal to 0, and so therefore the slope is infinite. In other words, a particle at rest, say at the origin, will just move upwards through the plane as time increases, not changing its position. A light ray moving along the positive x-axis will have a slope of +1. A light ray moving in the negative x direction will have a slope of -1. Lines with an absolute value of the slope greater than 1 corresponds to objects moving slower than the speed of light. In this case, the slope is 2, and so the velocity will be 1/2 the speed of light. This world line has a slope of -2, and so its velocity will be -1/2 the speed of light. World lines with an absolute value of their slope less than 1 will correspond to faster than light travel, which is forbidden in relativity. So the areas in the two shaded regions to the left and to the right of the origin cannot be accessed by a particle at the origin because it would require faster than light travel. Let's draw a space-time Minkowski diagram for the train experiment. We're only interested in what happens for time greater than or equal to 0, so we'll just use the upper half plane. So just as a reminder, we'll draw a little picture. We'll call the ground reference frame S and the train reference frame S prime. We first draw the events from the perspective of the train, so our coordinate axes will be x prime and ct prime. Let's assume the light source is at x prime equals 0 at time t prime equals 0. We'll also assume Mr. Red and Ms. Blue are 10 meters apart. Thus, they will each be 5 meters away from the light. We'll draw a mark where Ms. Blue is and a mark where Mr. Red is. Because Ms. Blue is at rest, her world line will move vertically upward. The same is true of Mr. Red. Once the light is turned on at time t prime equals 0, it will propagate to the right and to the left at the speed of light along diagonal lines with slope ±1. We'll call the point where the light ray intersects Ms. Blue's world line event A. And we'll call the point where Mr. Red's world line intersects the light ray event B. These two events correspond to the locations where the two observers see the light flash. As we can see, events A and B occur at the same time, where ct prime equals 5 meters. Thus, Mr. Red and Ms. Blue see the light flash simultaneously. We can write the space-time coordinates of event A as x prime sub A, ct prime sub A equals 5 meters, 5 meters. Similarly, the space-time coordinates of event B are x prime b equals -5 meters and ct prime b equals 5 meters. Now let's draw the space-time diagram from the perspective of observers on the ground. From their perspective, the train is length contracted, so the position of Ms. Blue is L/2 divided by gamma. This corresponds to about 4.33 meters. Mr. Red's coordinate will be will have the same magnitude but in the negative x direction. Each of their world lines will have a slope of 1 over beta, or 1 over 1/2, so 2. Because Einstein says the speed of light is constant for everyone, light rays will have a slope of plus or minus 1 from the ground frame of reference. We label events A and B as before. Event A corresponds to the point where Ms. Blue sees the light ray arrive at her position. Event B corresponds to Mr. Red seeing the light ray. So the diagram clearly shows that Mr. Red sees the light flash before Ms. Blue does. We can estimate the time at which he sees the ray by reading across from point B to the CT axis, and we see that it's just under 4 meters, it looks like. Similarly, we can read off the time that event A is by reading across to the CT axis, and it looks like it's just under 9 meters. So from a purely geometrical construction, we can clearly see why Mr. Red sees the light flash earlier than Ms. Blue does from the ground frame of reference. To find the time of event A, we need to find the intersection point of the orange light ray and the blue world line. The equation of the orange light ray is x equals ct, and the equation of the blue world line is x minus L0 over 2 gamma equals Vt. We'll plug x equals ct into the blue equation to write ct minus L0 over 2 gamma equals Vt. We can also write Vt as c times beta t to write the equation in terms of betas instead of v's. We'll pull out a c and group the t's on the same side of the equation to write c times 1 minus beta times t equals L0 over 2 gamma. Solving for ct gives, so we find that c times the time at event A equals L0 over 2 gamma times 1 minus beta. Plugging in values for this simulation of L0 equals 10 meters, beta equals 1/2, and gamma is 1.15, gives CTA as approximately 8.66 meters, which agrees with the position of the dashed line in the diagram. We'll now repeat the calculation for event B, which corresponds to Mr. Red seeing the light flash. The equation of the leftward moving light ray is x equals minus ct, and the equation of the red world line is x minus a minus L0 over 2 gamma equals Vt. Again, we substitute x equals minus ct into the red equation to write minus ct plus L0 over 2 gamma equals Vt. We substitute V equals c times beta to write the equation in terms of beta, group the t's together, factor out a c to write c times the quantity 1 minus beta times t equals L0 over 2 gamma. Solving for ct gives ct at event B equals L0 over 2 gamma times the quantity 1 plus beta. Plugging in L0 equals 10 meters, beta equals 1/2, and gamma equals 1.15 gives c t sub b is approximately 2.89 meters, which again is consistent with the dashed line in the figure. We now find the time difference between event A and event B. The position of Mr. Red initially is minus L0 over 2 gamma, taking into account length contraction. Let's go back and retrieve our results for events A and B. We can now subtract these two values to find the difference in time. Plugging in for C t sub A and C t sub B gives L0 over 2 gamma times 1 minus beta minus L0 over 2 gamma times the quantity 1 plus beta. We factor out an L0 over 2 gamma, put it over a common denominator, and realize that the denominator is the difference of two squares. This simplifies to L0 over 2 gamma times 2 beta over 1 minus beta squared. Because 1 over 1 minus beta squared is simply gamma squared, this term simplifies to L0 over 2 gamma times 2 times beta gamma squared, or L0 times beta gamma. Finally, let's calculate the slope of the line connecting events A and B. The slope is given by the change in height along the CT axis, so C delta t divided by delta x. We just found an expression for C delta t, which is L0 times beta gamma. We leave it as a homework problem for you to solve what delta x is, but it's equal to L0 gamma. The L0s and gammas cancel, and we find that the slope is simply beta. This line is interesting because it shows you the line through space-time where all the clocks in the moving reference frame will be synchronized. In other words, this is a line of constant t prime in the ct versus x space. So, in summary, we see that the timing of two events depends on the frame of reference from which they're observed. In the train frame of reference, Mr. Red and Ms. Blue observe the light flash at the same time. The events are simultaneous. In the ground frame, Mr. Red sees the flash before Ms. Blue with a time difference of C delta t equals L0 beta gamma as measured from the ground frame of reference. The line connecting events A and B is a line of constant t prime. Events along this line happen simultaneously in the train frame of reference S prime. If the train reversed directions to travel from right to left instead of left to right in the ground frame of reference, then event A would happen before event B. In the next lecture, we'll use these results to derive a more general set of transformation equations to go between two inertial reference frames. These are called the Lorentz transformations.